All right, hello everybody. Hope you had a great weekend. So homework there's a web work and a written homework due Wednesday night. I trust you have started that and worked a lot on that. It's too late to start. Of course, if you haven't started, you need to start immediately, but that's a fair amount of work, and you need to break that up and start it early so you can get some support maybe tomorrow and Wednesday. Get your questions answered. We've got today and Wednesday for lecture, and then Monday and Wednesday again next week, normal lecture, and then the final exam is that Thursday, a week from this Thursday. Thursday night at 7 p.m. is the final exam. And is that December 3rd? Is that what that Thursday is?
Yes. Yes, sir.
Yeah. Very good. And I'll get the prep materials up for the module, the final exam prep module. Get that all loaded up before the break this week. So if you want to get started studying, the final exam, we're going to keep all the percentages the same as what I promised you in the syllabus. I'm not gonna shuffle around percentages. So this will be like a final exam in terms of it'll have a higher weight than the previous exams. It'll be 2 hours, it'll be maybe a little bit longer, and then it'll be primarily on this new material, but that, like I've said before, that uses a lot of the previous material from the course. So in effect, it is comprehensive, emphasizing the new stuff. Okay, any questions on homework, class schedule, final exam, any of that? Okay, so we did Green's theorem. We talked about some examples of Green's theorem, and so now I want to look at new topics. One of my favorite topics. I really like this lecture today. Hope you enjoy it, because I sure do. It's cool stuff. So here we go. Oh, before I do that, in the web work, they use a notation that I have never really used. Let's get this up here. Yeah, so in the web work, they use a notation that I have, and I posted an announcement a couple weeks ago about it, but I just want to point it out during live lecture here, that you often will see a form like this for line integrals on Webwork. And this is no different. It's just a different notation, but mathematically it's the same as what we've been doing for line integrals, because you can see if this was a dot product, if this came from a dot product, what dot product would it come from?
Partial derivative of the function with respect to x and then with respect to y.
No, these aren't partial derivatives. These are products. This is p times dx plus q times dy. So what dot product would this represent?
Oh, so yeah.
Dot dx dy.
Yeah, so this would be pq dot dx dy. That's what this is exactly. These are exactly the same. Exactly the same, right? Because if you did the dot product, you get p times dx plus q times dy. Well, pq, that's just simply the vector field. And what is dx dy?
dr.
Yeah, so that's dr. Now, the way we're used to seeing dr is this way. dx dt, dy dt, then that vector times dt. But so that's how we see dr. Well, that's exactly the same as this. It's exactly the same as dx dy. But this is just writing it in terms of t. So whenever you see this notation, p dx plus q dy, it's this. It's the same, exact same line integral of a vector field that we've been doing. So if you want to start out by writing it this way, then you're welcome to do that. But I just don't want that to throw you off like, oh, we never did that. Well, yeah, it's just a couple mathematical steps away from exactly what we did. Okay, so just be aware of that. And then I also, like I said, there's an announcement from 2 or 3 weeks ago that kind of reiterates this conversation. Any questions on that? All right. Okay, so we've been talking about vector fields. Vector field, what's a vector field? For every location, either in R2 or R3, there's an associated vector. So the vector field function assigns a vector to every location. So what do vector fields have to do with rate of change? So according to what we've talked about, what does a vector field have to do with rate of change? Anyway, what's that?
Gradient.
Okay, so gradient fields are a certain, a special type of vector fields are gradient fields.
But like, I guess I mean like those gradients are rates of change, aren't they?
Okay, right.
Like
Of what? Yes, exactly. So a gradient field represents, those vectors represent rate of change. Okay, so rate of change of what?
Like the z height of the function, I guess.
Uh, yeah, what, yes.
The original function,
What's that?
the f, the original function, like the f.
Yeah, right.
Is the
So
actual-
if it's a gradient field, then what do we say? A gradient field means that f is the gradient of some what multivariable function, right? So this field, this vector valued function, is the gradient of some multivariable function, real valued function. So if we have some function f, then the gradient of f would be a vector field in the xy plane. And what's true about all those vectors in the xy plane? How do they relate to f?
They all point in the direction of the greatest rate of change.
That's right. So that gradient field in the xy plane is like an image of the rate of change of this surface. They give the direction of max rate of change and the magnitude of the max rate of change at every point on the surface. So this gradient field for the surface I drew may look something like this, right? Higher rate of change, and the change decreases, so going up this way, but decreasing rate of change till you get to some like kind of maximum here. And then now the rate of change over here is higher away from the maximum, and as you get closer to the maximum, the rate of change decreases. So I'm sketching kind of the gradient field for f there. So that gradient field is a representation of the rate of change of the original function f for every point on that surface. Okay, so that's been our conversation how vector fields relate to rate of change. If you have a gradient field, that itself is representing the rate of change of a multivariable function. Okay, so then a new question is, which we haven't talked about, is what is the rate of change of a vector field? So vector fields themselves are functions, right? So for instance, right, they take what? They take location, and for every location they spit out what? At every location, a vector field,
Vector.
yeah, it gives a vector. So this is a multivariable vector valued function. It takes more than one input, in this case a location in R3, And for every location R3, it spits out a particular vector such that the components of that vector depend on the location. Right? So it itself is a function. A vector field is a function. Location gives vector. And so as a function, it itself has rate of change. So today we're going to start investigating what is the rate of change of a vector field. Well, it turns out that there are actually two distinct varieties of rate of change of a vector field. Not just one, but two different types of rate of change. And so the first type of rate of change is called curl. Curl is rotational rate of change. So what we're going to do here to figure out what this thing curl is, this rotational rate of change of a vector field, is we're going to look at a small element, dA, in that vector field. So we're going to call the vector field, we're going to use our standard, like our generic components P and Q. So P is the X component of each vector, Q is the Y component of every vector. And we're going to look at a little element, a little dA element. We saw this with double integrals. We were looking at these elements. So I'm taking just a little element, a dA element, and kind of scaling it up here, so it's nice and big for us to work on. But this is just a very small element in the vector field, and so as such, it's surrounded by vectors. And so for a very small change in x, there could be a variation in the vector. So I'm calling that f to the left and f to the right. So this is the value, the vector of the field just to the left of a little dx, and then just to the right. So it could be a little change in the vector field for a change in dx. Likewise, b for bottom, t for top. For a change dy through that vector field, there could be a little change in the vector field, right? A small change to that vector as you move vertically. Okay? So just some setup before we get into it. We're going to use a convention that counterclockwise rotation is positive rate of change. So curl is rotational rate of change, and so we need to define what positive is. So positive is going to be counterclockwise. So positive curl is going to be counterclockwise. All right, so now let's see. We're going to take a look at these vectors, and so namely the horizontal components, which are the P, right? The horizontal components of the vectors are the P, the X component. And so then I'm going to have P top, P right, P left, P bottom, okay? And then I'm going to have vertical components, and those are the Q's, right? So I'm going to have Q top, Q right, Q left, Q bottom. So I'm writing these vectors that are kind of surrounding, that are right around our element in terms of their horizontal and vertical components. And so we're asking about rotation. So what components, so I'm looking just at the top and bottom now, and I want to ask myself, which of these components of the top and bottom vectors are you going to contribute to rotation around this point? So one thing you can do is think of this element as a spinner. Now the element itself cannot spin, but it's kind of helpful to imagine this. So if that element could spin, according to the vectors around it, so which of these components, QT, PT, QB, and PB, are going to cause this thing to spin? So if we're applying the top vector, if we apply it right there, and apply the bottom vector right there, which of those four components are going to cause this thing to spin around the center point? So let's just go with each one. What about QT? So QT is you're pulling straight up on this point. Is that going to cause this thing to rotate, spin?
No.
What about PT? So I'm going to pull right here, PT. What about pulling that way? Is it going to cause it to spin?
Yeah.
You should be thinking yes. If you grab on this point, this is a spinner, you grab on this point and you pull this way, that thing's going to turn. But if you grab on this point and pull up, it's not going to turn. What about down here? Q or B below? Going to cause this thing to turn.
P.
P. So Q, top and bottom, is just kind of pushing against this spot. It's not going to cause any rotation. But the P's, the horizontal components, cause the rotation. Does everybody see that? It's really important to recognize that. So we won't, if we're talking about rotation, then we don't care about the Q. Don't miss this. Here we go. Watch, ready? So we don't care about the Q's. We want those gone. All we care about then for the top and bottom vectors is the horizontal components. So what do we have? We have a change in Y from the bottom to the top affecting a change in P. So what's the key? How do we determine what change in P we have given that change in Y? So that little equation should look familiar. Given a change in the independent, in this case Y, what is the key to determining the resulting change in this horizontal purple vector? Somebody please know.
X component.
What's it?
Vectors.
Well, P's are the X components, but given a little change in an input variable, what's the key quantity that gives us the resulting change in the output variable?
Partial derivative.
Good. It's derivative, right? So it's a rate of change, right? So the rate of change is what tells us how much P changes output for a change in Y. We worked hard on that. I don't know if you remember. We worked hard on partial derivative. So which partial derivative do we need if it's the change in P coming from a change in Y?
So with respect to Y.
Yeah, so it's going to be, that will be that's the partial derivative of P with respect to Y. That's the key to getting changes in P given a change in Y. Okay, now let's look at right and left rotation. Well, no, before we do that, let's go back. And let's talk about, we said what? Counterclockwise rotation is positive. If you had, for an increasing Y, if you had increasing P, that's what I'm showing here, right? This is a little bit bigger than this one. Would those two vectors cause clockwise or counterclockwise rotation? The top vector to the right is larger in magnitude than the bottom vector to the right. What will be the result? Clockwise or counterclockwise rotation?
Clockwise.
Someone's saying clockwise. Rest of you?
Clockwise.
Yeah. If this one's bigger, this one's going to win, right? This is going to win. These are fighting against each other in terms of turning. Pulling to the bottom to the right versus pulling the top to the right. This one's going to win out because it's a bigger vector, so we're going to get what? Clockwise rotation. So a positive value of the rate of change, the partial derivative, results in clockwise rotation. Is that positive or negative curl?
Negative.
That's negative curl. So if we want to talk about how this contributes to positive curl, we're going to have to multiply that by -1 for positive curl. Does it make sense?
No.
Because if it's positive, it's creating clockwise rotation. That's what we're seeing here. A positive dP from a positive dy is creating clockwise rotation. Do you see that much?
Yeah.
But positive curl is counterclockwise.
Oh, okay.
If we want positive curl to be counterclockwise, then the contribution of this to positive curl has to be the opposite of it.
Yeah, that's helpful.
Okay, cool.
Thank you.
Very good. All right, so I don't want that. Okay, so what about the right and left?
would it be just the Q's that cause rotation?
So he's saying just the Q's. So let's take a look. This vector P pushing on this cause rotation around this point? Pushing against right there, that point?
No.
No. What about pulling with this P over here?
No.
No. What about if I take this, grab this point and I pull up according to QL? Make rotation?
Yes.
Yes, right? What about QR? If I take this point and I pull up this way, going to cause rotation?
Yes.
Yes. Okay. So for a change in X, what's going to affect rotation? The change in Q is going to affect rotation. P is going to have nothing to do with rotation here. So same thing. Now we're going to get rid of the P's, hold on to the Q's, and then what will be my key in terms of rate of change?
Partial derivative of Q in terms of X.
That's right. Partial derivative of Q with respect to X. Now what about this? So for a positive change in X and a positive change in Q, will that affect positive or clockwise or counterclockwise rotation?
Would this be counterclockwise?
Yeah, this is going to win, right? QR is bigger. So here's QR pulling this way like this, right in this point. QL is smaller. So this one's going to win and it's going to pull this, turn this thing counterclockwise.
Is your like multiplying by -1 for the dp like specific to this example? Because like in this example, the clockwise rotation from at the top is like more than the one from the bottom, so you have to multiply by -1. Like in other examples, would the bottom one be more and then?
Yeah, but if the bottom was more, then you'd have counterclockwise rotation, but dp would be negative. So
Okay.
does that make sense? So I'm making dy positive and dp positive.
Yeah.
So when dy is positive and dp is positive, this will be positive, will be clockwise rotation. If I mess with this and make dp negative, then this positive, then this will be negative and give counterclockwise.
I think I don't get like how the dp is negative if the bottom one is bigger.
Because for a change in y, for a positive change in y up, you have a decrease in p. P is bigger down here than here, so dp is negative.
Oh, it's the change in p from top to
dp,
bottom.
yeah, the
Okay.
change.
Okay. I wasn't looking at both vectors together.
Okay, so then for the Q's, this wins the fight of trying to turn this thing, and it turns counterclockwise. So for a positive dx and a positive dq, you get counterclockwise rotation, which agrees with the curl, so we're not going to do anything to that. When that's positive, we get positive curl. So the total curl is going to be the combined effect of the p's top and bottom and the q's left and right. So what? We're going to have partial of q with respect to x and the opposite of the partial of p with respect to y, joining forces to make the total rotational rate at this point.
Professor?
Yeah.
So is this then what Green's theorem is?
Right.
Is this the curl?
Exactly. So in Green's theorem, we said that integrand for the double integral was a rate of change. Well, it's rotational rate of change, and this is where it comes. This was where it comes from. This is a rotational rate of change. It comes from the horizontal components of vectors above and below a point, and the vertical components to the left and right, and then the combined effect of those two things. So that's what q with respect to x and p minus p with respect to y is combined effect of rotational rate of change, or the combined effect of the vectors all around this element contributing to rotation. And so that's what we call the curl. But The curl is actually a vector. So so far, this is just the magnitude. This qx minus py is just the magnitude. Curl is actually a vector. So if we're dealing with the right-hand rule, what vector direction represents this counterclockwise rotation? What vector direction according to the right-hand rule?
Is it like out of the page?
Right. What direction would that be? So we're in the xy plane here. What direction would be coming straight out at us? According to the right-hand rule, curl your fingers counterclockwise and your thumb is pointing right at you. What direction is that?
The positive z direction.
Right. Okay. So the curl of f is a vector, and it's at a point. Okay, so the curl of f, this is the strength of rotation, is the magnitude of it. And then the direction is orthogonal to the plane of rotation. That's key. The vector direction of rotation is actually orthogonal, according to the right-hand rule, orthogonal to the plane in which the rotation is occurring. Super important. So curl is a vector, and it's a vector function. As soon as we move to a new point, we have a different curl, a different strength of rotation, maybe a different direction of rotation. Okay, so curl is a function, and it's a vector function. Now every point in the F vector field has a curl vector. So it itself is a vector field, curl, which is a pointwise vector function. Okay, does that make sense? Any questions? So this is just dealing with the xy plane. So in R3, you have contributions to the curl in parallel to three planes. This is one of them, right? So this is the contribution of the curl parallel for rotation parallel to the xy plane, or in the z direction. Then we'll have two more of those for curl in space. So we'll look at one more, which is exactly the same as this, with just different variables. And we won't do the third one. Okay, any questions before we move on from x and y?
Professor, back in regards to Green's theorem, is it just then the double integral of the curl with dA meaning like k almost?
No, dA isn't k. dA is it's actually the area of this.
Okay, I guess what I meant, like, 'cause I know sometimes you use dA to mean like the vector orthogonal to some given area A. I guess that's what I was thinking.
No, that's not that. Well, that's an area vector. We're going to do that later, if we even get to that. But no, dA has always meant that a little area of a little element. It's not a vector. dA is not a vector. It's an area. It's a little element, and it's area.
Okay, thank you.
So this is not like Green's theorem, like Qx. This is not dA. This is the direction of the curl, whereas dA would be multiplying by little areas. So that's two different things. Other questions? All right. So curl in R3. So now we have a three-dimensional element. Now we're looking in our standard view, the x-axis coming out at us, y to the right, z up. And here's an element in R3, and so since y is to the right, this bottom here is the dy, and this up and down is dz now. Okay, so everything is the same, but now our horizontal components, so if f is PQR now, not just PQ, but our vector field is PQR. So what are these horizontal components? Are they P, Q, or R? The horizontal components.
P and Q.
Nope. Just the horizontal components of these vectors.
Would that be P?
No, it's the horizontal. Now, looking at this view, like an R3 is Y, right?
Oh, so just Q.
Yeah, it'd be
right?
Q, right? Does everyone see that? In our vector field, the X component's P, the Y component is Q, and the Z component is R. And so now I'm looking just at this, like this is like the parallel to the YZ plane. So if I'm parallel to the YZ plane, horizontal is Q, right? Horizontal is Q in the Y direction. There is another horizontal that's going front and back. Okay, so we already dealt with X and Y, right? So this is this up here, like this is like the XY. This plane of rotation is what we dealt with in the previous slide. It would be the plane parallel to X and Y. So now we're looking at planes parallel to Y and Z. So a horizontal component is Y or Q, and then vertical component is our R components of those vectors. So just like before, looking at a change in Z, what's going to contribute? The Q's or the R's are going to contribute to rotation. The Q's or the R's?
Be R's.
Okay, so given a change in Z, looking at the top and bottom vectors, the R's are going to contribute to rotation. Does everyone agree with that?
Oh, it would be Q.
Yeah, the Q's, right? R's would be like pulling straight up on this thing at that point. That's not going to cause this element to rotate. But the Q is going to cause it to rotate, right? You're pulling it this way, and it's going to cause it to rotate. Everybody see that? So, and then similarly, the left and right vectors, what's going to cause rotation of this element? The Q's or the R's?
R.
The R's, right? The Q's are just going to like push and pull on it and won't cause it to rotate. But the R, if you grab right this point right here, and you pulled with the R component, it's going to cause it to turn. Likewise, if you pulled at this point right here, or no, back here, if you pulled on that point right there with this R vector, it's going to cause it to turn. All right, so then we're going to have partial derivatives, right? So for a change in Z, we care about how Q changes. And so that's going to be the partial derivative of Q with respect to Z. And then for a change in Y, going across from left to right, we care about the change in R. So it's going to be those partial derivatives this time. And it's going to be the opposite of Q with respect to Z to make it for positive curl, and positive R with respect to Y, just like before. So it's going to be what? The magnitude is going to be partial derivative of R with respect to Y minus Q with respect to Z. And then that will be in the I direction, right? Right-hand rule. So positive curl will be like this, around this point. By the right-hand rule, direction is in the I coming right out at us. So in R3, there'll be a contribution to the curl from each of the three planes, parallel to the XY plane. Or sorry, parallel to the coordinate planes. There'll be the one we did in the previous page, parallel to the XY plane, the vector of which will be in the Z direction. There'll be a rotation parallel to the YZ plane, like we're showing here. And that direction of that vector will be in the I direction. And then there'll be one more, which we won't do this whole thing again, but it'll be rotation parallel to the XZ plane, which will have direction J, orthogonal to the plane of rotation.
would you have to multiply dq over dz by -1 because it would be rotating clockwise?
Yeah, so that's right here. That's what we're showing right there.
Oh,
Yep,
thank you.
it's got the -1 on it right there. Yep, exactly. Okay. So, finding the curl algebraically. So it's like we said, it's a new vector function. It's a new vector field from the old one, right? So we start with our vector field PQR. The curl is a new vector field, right? It is also assigning a vector to every point. It's just that that vector now is representing the rate of change of rotation at that point. Okay, so the curl is a new vector field taken from the previous vector field, but it's representing the rate of change of rotation at every point, those vectors. So to calculate it algebraically, we can do the same. We can do the same algorithm that we did for cross product. So here, F, you put F in the third row, put your standard unit basis vectors in the first row, I, J, K, and then put the partial operators in the second row. And so this is our gradient. So our gradient is like a vector of operators. So we're doing the cross product of the gradient operators with F, but it's not going to be multiplication, it's going to be executing the partial derivative. So what are we going to get? So I, we're going to get the partial derivative of R with respect to Y minus the partial derivative of Q with respect to Z. So going down, the positive down to the right, negative down to the left. And then J will be the partial of P with respect to Z, going down to the right, minus, down to the left, partial of R with respect to X. And then K, going down to the right, partial of Q with respect to X, minus P, that's the familiar one, minus P with respect to Y. So when you do that whole algorithm, you get the formula for the curl. So when you're finding the curl of an actual vector function algebraically, I go back and do this algorithm every time. I set up the matrix, and I execute the partial derivatives and subtract. Okay, you'll get, this is the same formula you'll get every time. I just, rather than try to memorize the formula and plug it into the formula, I just set up the matrix and execute the algorithm when I'm doing a particular example. We'll do one later in class. But here's the formula for the curl.
Professor?
Yeah.
For the test, do we need to be able to, will we get a form with this formula, or do we need to be able to derive this like you, or memorize it like you said?
No, so whenever I find a curl, I always use the algorithm. I always do it. So this is the formula you get. This is the formula for the curl, but you don't have to memorize it because you can just execute the algorithm. And I think that's easier. Does that answer it?
Yeah, so we won't be given it. We'll have to be able to, get it by doing.
But you have a particular example, right? You'll have function. You'll have a vector field here, and so you'll actually be doing these partial derivatives and getting expressions by doing the cross product.
Okay, thank you.
Yep. Okay, so what is the curl? The curl is a vector. It's a new vector function from the old vector function, right? It's a new vector field taken from the old vector field, but now the vectors are giving what? The magnitude of those vectors give rotational rate of change of the original vector field, and the direction of those curl vectors are orthogonal to whatever the plane of rotation is. So this is a new vector field derived from F. It's just that these new vectors are giving, magnitude is giving the rotational rate of change, and the direction is showing you orthogonal to the plane of rotation. So here's a big takeaway of this. Huge takeaway. Really important. Curl is a function. Rotational rate is a point-wise phenomenon. Meaning, it varies depending on the specific location in the field. Every point has an associated curl vector with it, and that is the rotational rate of change at that point. And as soon as if you move away to a different point, you have a new value of curl, or you could. All right, let's look at an example. This one. So here's a vector field. And it's showing you kind of some of the vectors in that vector field. So what about the curl of this vector field?
It's counterclockwise.
So we got counterclockwise rotation, right, in this field. So curl is?
Positive.
So that's our conjecture. Is that everyone's kind of intuition here? Since this field is kind of rotating counterclockwise, the curl is positive. I feel okay?
Yes.
All right, so let's investigate here a little bit closer. Let's pick a point right here. And let's take a look at the vectors kind of around that. So let's look at horizontal components first. Here's this horizontal component. Here's the next one, a little bit less. Next one up is a little bit less. Next one up is a little bit less. So just looking at the horizontal components above and below, so we got a kind of a larger vector to the left below and a smaller vector to the left above. Does that indicate clockwise or counterclockwise rotation?
Clockwise.
We have a vote for clockwise. Which is going to win? So this is going to be a war against rotation, right? This is going to try to turn up here, try to turn it counterclockwise. This one down here is going to try to turn counterclockwise. Sorry. Vector on the top is trying for counterclockwise. The vector on the bottom is turning clockwise. Which one's going to win?
The biggest one is
The biggest one, right? The one on the bottom. Okay, so that's indicating clockwise rotation. All right, let's look at the vertical components. Biggest here. Oh, I should have put the point over here, sorry. I meant to put the point here. Same difference. Okay, so biggest there, and then getting smaller this way. So what about here? So I got this vector on the left side is bigger than this one on the right. What's that going to indicate? Clockwise or counterclockwise? So this vector here is trying to rotate it clockwise, and this vector here is trying to rotate counterclockwise. Which one wins?
Clockwise.
Clockwise. Uh-oh. So both the vectors above and below and the vectors left and right, by their magnitudes, are indicating clockwise rotation. I thought you said, so what would the curl be?
It should be positive just by looking at it. Because kind of like it looks like it's circulating counterclockwise.
What is the curl at this point? Positive or negative?
Negative.
Negative. The vectors above and below are making this thing turn clockwise. The vectors left and right are making this thing turn clockwise. So what's happening here? I thought it was supposed to be positive. This is negative curl.
So they're like opposing. They're like functions and that they're curling, but it's just going the opposite. And it's why it kind of like stop curling near the edges.
No. I mean that's not the reason for our conflict here. What's the reason for our conflict here? We said, oh, the curl is definitely positive. We got counterclockwise rotation. But then when we looked at the vectors surrounding this point, all the vectors surrounding this point indicate clockwise rotation. What is curl? Did we learn anything from the previous screen?
It's a function.
It's a function. And functions are
Pointwise.
pointwise phenomenon. All right. What about the fact that this thing globally turns in a big counterclockwise circle when you look at the whole thing? Is that what curl is about?
No.
No. Curl is a function of location. It's a pointwise phenomenon. As soon as you move to somewhere else, you can get a different curl.
So if we chose a point that was on the bottom right or bottom left, would that point's curl be positive?
I don't know. We'd have to do it. We'd have to do what we did here. So it's positive. It's possible. But the point is here, like if this was like a big like whirlpool, okay, and you put a little flywheel in the whirlpool, so this flywheel is like a little, it can rotate according to current, and it can move according to current. So which way is it going to move according to the current?
Counterclockwise.
Counterclockwise in a big circle, right? It's gonna move around in a big circle. But according to what we analyzed here, how is it going to rotate?
Clockwise.
It's going to rotate around like this as it moves. So as it's moving in a big counterclockwise circle, it can be rotating clockwise, like some kind of amusement park ride or something like that. So, not right. Curl is not a global phenomenon. It's a pointwise phenomenon. And even though it looks like everything's rotating around, it is counterclockwise, you could have any kind of rotation pointwise, regardless of the global rotation. So the curl is negative, at least at this point. Curl is negative. Okay, so we're gonna run over a little bit. Sorry about that, but we gotta do it. We got one more example. Any questions on this example?
So if you were to, so based on this whole vector field, it's going counterclockwise in this case. But when if you have the, say, function of this, if you have the function for curl and point whatever, and plug in whatever point in, it would then give you which direction it curls, be it clockwise or counterclockwise.
Right, exactly.
Okay.
Yeah, so well, what would tell you is whether it would be positive z or positive k or negative k, right? So this is just an xy vector field. So the curl is going to either be pointing in the negative k direction or the positive k direction. In this case, if you plug this point in to the curl, you're going to get what? Negative k, because it's actually turning clockwise at that point.
Right.
Meaning the curl is less than 0. All right, quickly, one more thing here. I wanted to show you how to do the algorithm. So here's another one. Here's another one that has globally, it has a clockwise rotation. But that does not tell you anything about the curl, as we just saw in the last example. So let's actually find the curl for this one. So we would do ijk, and then the gradient operator, which is partial derivatives operating, and then negative y x squared, no, x to the minus 2, and then x to the minus 1, 0. Okay, so curl. So the curl of f is going to be, this is f, this is our f in the third row. The curl of f is going to be, so the I will be, it'll be this the partial derivative of 0 with respect to y, positive, minus, coming this way, down to the left, the partial derivative of x to the minus 1 with respect to z. So what will we get for the I component? 0 and 0, right? Partial derivative of x to the minus 1 with respect to z is 0. What about the y component? So down to the right is going to be coming down this way. It's going to be the partial derivative of this expression here with respect to z. There's no z's in it, so it'll be 0. Minus the partial derivative coming down to the left. Partial derivative of 0 with respect to x will also be 0. Now, that's to be expected anyway in an xy vector field, right? So if it's just an xy vector field, we know that it'll be in either the negative k or positive k direction. So those were expected. So here's where the curl comes in. The actual, going down to the right, it'll be the partial derivative of x to the minus 1 with respect to x, which will be minus x to the minus 2. Minus, going down to the left, the partial derivative of that expression with respect to y. What will that be? Minus
x to the negative
x to the
2.
minus 2. What is our z component?
0.
That's 0. So for this vector field, the curl is the 0 vector. Everywhere. Everywhere, and so this is called irrotational. There's no tendency of rotation in this vector field. Even though the whole thing is turning in a big counterclockwise loop, at every point in this vector field, there's no rotation pointwise. And notice, what is this? This was qx minus py. And that's what our z component was. When qx minus py is 0, what can you say?
It's a gradient field.
That's right. Irrotational fields are conservative. And it's a gradient field. Okay, questions on that?
So, if I'm getting this correctly, with the matrix that you set up with the IJK, all that, what you're doing is basic in linear algebra. You're just taking the determinant of each one and figuring.
Yeah, it's the same as remember when we did the cross product?
Right.
This is a cross product. It's the cross product of the gradient operator and your vector field components. Instead of multiplying, you're taking partial derivatives.
Right. So okay, yeah.
But it's the same. Yeah, it is the cross product.
Okay.
It is the gradient cross f is the curl.
Okay.
And for this particular field, we got that the curl was 0 everywhere. That means it's an irrotational field. At every point in this field, there's no tendency of rotation. 0 rotation at every point.
Right. Yep.
And that's synonymous with it being conservative field or gradient field.